Hello, my name is Hans-Peter Arp, and I'm the Deputy Coordinator of the research project ZeroPM, and I am thrilled to be talking with Professor Ian Cousins from Stockholm University, who is one of our central researchers in ZeroPM as part of our work on alternatives assessment. However, the main reason I'm talking with him today is, wow, Ian and his colleagues recently published a paper that has been an absolute blockbuster. It has been picked up by every major news outlet, and since its publication about 2 weeks ago, it has been downloaded over 150,000 times, which is insane for a research paper. If this was a book, it would be an international bestseller. The paper is called Outside the Safe Operating Space of a New Planetary Boundary for PFAS. The paper talks about how PFAS levels in rain, water, and soils have exceeded safe levels for the planet, and how their concentrations are slowly reversible only. Now, an issue, though, is that a lot of media has gotten some of the science wrong, some of the science right, and there's been issues with that. So we felt it worth doing a breakdown of the paper, asking some key questions to clarify the science and some of the key points. So I'm going to ask Ian some questions now. So first, Ian, hi and welcome. Thanks for doing this. And just off the bat, what have the past couple of weeks been like for you to see this reaction to your paper?
Yeah, thanks. Hi, Hans-Peter. It's been quite surprising that we got such a huge media response, and it's been very intense the last 2 weeks. I wasn't really ready for the live TV, live radio, and all of the emails. So it's been a learning experience, I would say, for me.
I can only imagine. This is not typical, like a scientist's normal day to suddenly become an overnight celebrity almost. So great. But let's get into the paper. So these are questions that people might have, especially at different levels of knowledge about what they know about PFAS and what was said in your paper. But I think it's important that we start with the basics, since we have such a large audience, I hope. First, what are PFAS, and maybe more specifically, which PFAS did you look at in your paper?
Well, PFAS, these are man-made substances. There's a large group of man-made substances, there's several thousand substances actually, and they were first manufactured in the 1950s, so they've been used for about 70 years in industrial processes and also in consumer products. So they have been used in the manufacture of PTFE, polytetrafluoroethylene, which is often known by its trade name, Teflon. But they've also been used in common consumer products like water and stain repellency for outdoor clothing and equipment, carpets, and also in firefighting foams and in food packaging, etc., etc., etc. There's over 200 different uses of PFAS, and there are many thousands of substances in the class. And these substances are all fluorinated, highly fluorinated, and this makes them extremely persistent in the environment. They're not expected to degrade at all in the environment, which has given them the nickname the forever chemicals. And some of them are also bicumulative. That means they accumulate in concentrations in wildlife and humans at higher concentrations than in the environment in which these wildlife or humans reside. And they also can have a whole range of different toxic effects. And so some of these substances are of very high concern, and some of them have been heavily regulated, and some of them have not. Some of them continue to be used in quite high quantities.
No, great. And so you said like there was several, like thousands of PFAS, but did you like look at all of those PFAS or just some of them?
In this paper, we looked at just 4 PFAS, and these are the ones that we have information on the toxicity. And unfortunately, we only have really detailed information on the toxicity of a few PFAS. And these PFAS are also the ones which are have been heavily regulated, and are probably the most famous, I guess, in the PFAS class. These include PFOS, PFOA, and also 2 substances very related to these 2 substances. So the hexane sulfonate and the nonanoic acid, which has 9 carbons. So these four PFAS are really kind of notorious in the class, and have been shown to be toxic and to accumulate in humans and like all other PFAS, are extremely persistent. So these are the ones we focused on in the paper.
Yes, quite. Yeah, the ones that we have the most data on, absolutely. That makes total sense. And as you said, there's a lot of data gaps for the other PFAS. Usually the only thing we know is they're persistent, but we don't know much else for many of them. So in your paper, it got a lot of headlines, but maybe in your words, what are the main messages?
Well, we kind of knew what the levels of PFAS were in different environmental media, and we've been sort of monitoring them for ourselves in rainwater, but also in other media over the years. And so what we have noticed is that the levels in the environment of these 4 PFAS I mentioned earlier have been relatively stable in the environment. So in rainwater, we have seen the levels over the last 10-15 years to be reasonably stable. But what has happened is that our knowledge of toxicity has really increased in the last 20 years since we first started to study these substances. And so what's happened is that environmental or sort of health advisories or guidelines for different environmental media have actually dropped over time enormously. In the case of drinking water guidelines, for example, they've dropped by millions of times since the first guideline was set in 2002 until today. So, and this is just, as I say, has an increased understanding of all of the different effects that these substances can have, and changes in the way we have assessed them over time. So, and the latest guidelines, I started to realise that the latest guidelines that have been coming out in the last few years were actually below the ambient levels of PFAS in the environment. So it's like, oh, how are we going to ever achieve these guidelines? If the background or ambient levels are above these guidelines. So this is what we really wanted to point out, that it's going to be impossible to achieve these guidelines for soil, for drinking water, for surface waters, because these chemicals are anyway already everywhere at levels above this, and they're going to continue to be at these levels above these guidelines for some time to come.
Yeah, so with the background levels that we just find in water, soil, rain everywhere exceeding these now what is known as a safe level, yeah, that probably leads us right into the next question, or the title of the paper, and that you said that they exceeded a planetary boundary for a safe operating space. So is that what this means, that we've exceeded the background level and it's going to be this way for some time? Is that what you mean by that?
Yeah, well, first of all, just a little background to the planetary boundaries concept is like, like you say, we're trying to define a safe operating space for humanity. And, there are 9 different boundaries that have been proposed for the planetary boundaries concept. And one of those boundaries is chemical pollution, which has been renamed as novel entities. And there are other boundaries for things like climate change and biodiversity loss and ozone hole, ozone layer depletion, and so on. But the people have looked at the chemical pollution boundary and tried to analyse that and see whether it's being exceeded or not. So we're interested. We've also attempted that previously. And so I was interested in that concept, and so what I thought was, yeah, well, let's look at PFAS and try and see whether the planetary boundaries have been exceeded just for these 4 PFAS. And so my idea was to see whether, if the ambient levels are above these health advisories everywhere, and in the case of PFOA, the rainwater levels everywhere on the planet are above the new drinking water advisory that was set by the US EPA. So even on the Tibetan Plateau and in Antarctica, the precipitation there is actually above the health advisory. So it basically means that you cannot escape being exposed to these chemicals at levels which could be considered unsafe. Wherever you are on the planet, which makes the planet a pretty inhospitable place. And going forward, we just have to the other important part of the planetary boundaries is that it's irreversible, that we just have to, well, or very poorly reversible. The only thing we can do is just wait. And as we've seen that the levels in rainwater haven't really dropped in the last 10 to 15 years, we don't expect them to drop in the next 10 to 15 years. And it's difficult to know exactly what the timescale of recovery is, but we're thinking decades. Because these chemicals are cycling around between the surface and the atmosphere, and the only way they're not going to be degraded. The only way that their levels can be reduced is if they're diluted into the deep oceans. And this is we know that mixing from the surface ocean into the deep ocean is a very slow process, which is going to take decades. So we think we are living on a planet now where our environmental resources are irreversibly contaminated with PFAS, which makes them unsafe to use, and that this is going to be the situation for some time to come. So we think, the planetary boundary has been exceeded just for these 4 PFAS.
Yeah, and you mentioned that our only chance left of dilution is the deep ocean, and this is a complex mechanism, but we have to also counterbalance with the fact that there's still a lot of legacy sources of these for PFAS, right? So we still expect ongoing emissions from certain areas.
Yeah, there was lots of contamination hotspots where these chemicals are going to leak out, and there are sort of landfill sites where these so-called volatile precursors can volatilize and then degrade into the atmosphere into these substances. That's pretty technical science, but there's also some ongoing emissions in Asia, especially in China, of some of these legacy compounds, and these are not staying in China, these are spreading around the world as well. So we can definitely put pressure on China, we can clean up all of these contamination hotspots. So we can do something to reduce some of these levels. But we can't clean up the whole planet. We can't clean up all the soils, and we can't clean up all the rain and the whole atmosphere. So that's we're just going to have to live with this long-term, low-level exposure.
Yes, and I think also when you explained about the planetary boundaries, you mentioned another one being the hole in the ozone layer, and I think that's a good example, because this was also something that exceeded a boundary, and to create a ozone layer that was too thin, that it was making holes, a huge hole in the Antarctic. And all we could do now is phase out those chemicals and wait for the effects of them to slowly decrease. And not only now, decades later, we start to see that the ozone layer is starting to heal itself, but it's still not where we want it to be, and we had to do a lot of work to get to this point. But maybe we'll go to that later. But I think that's a very helpful metaphor, because it's very parallel.
There's an important pattern there. It's the high persistence of these substances and a lack of knowledge about their effects. And when CFCs were first introduced into the environment, when they were first measured in the environment by James Lovelock, who died recently. He actually made a mistake and said that there's no conceivable toxic hazard associated with these substances, which he later said was a big regret, that he had. But and then a few years later, they found another effect, which wasn't a toxic effect, which was the depletion of the ozone layer. So that you have to be aware with toxic chemicals that you could then later discover an effect, and those chemicals are then poorly reversible.
Yes, absolutely. No, and this brings up also the precautionary principle with these persistent substances. We can't assume that they're safe, because too many times the persistent substances have been found eventually to be toxic. And as you said, decades after, prominent scientists concluded that they were not toxic. So this is a pattern we've seen repeat. And great. And so my next question is, so a lot of people now might be concerned that they're exposed to this PFAS. So what are the health concerns to human health, and maybe also to the environment, of PFAS?
Well, there's a range of different effects associated with PFAS at higher exposure levels. So around some of these manufacturing plants where they've made PTFE, there's been some good epidemiological studies that have found links between the high exposure to different kinds of cancer, so testicular cancer and kidney cancer, and also thyroid disease, diagnosed high cholesterol, and so on. So there are, and then there are also effects like development toxicity. But the effect that's really driven these guidelines down recently is some work by Philippe Grandjean. He was actually a Danish scientist, and he did some research on the Faroe Islands, and the research that he did showed that vaccines would become less effective due to exposure to PFAS, so especially in children. So vaccination against common diseases like diphtheria and tetanus, and then that these vaccinations would be less effective because the children were shown to have a lower ability to produce antibodies. And so, you know, this has really been a big concern. This is so-called immunotoxicity, and this has driven the what's considered the safe levels now in drinking water down to almost unprecedented low levels in, you know, for PFOA 4 picograms per litre, which is parts per quadrillion, which is challenging to measure. So, yeah.
Yeah, well, having said that about these toxic effects and that these levels exceed in rain, I think one of the key questions, the blockbuster question that people are getting from your paper is this one. Maybe you can answer it. Is it safe to drink rainwater?
Yeah, well, this is a tricky question. I don't think that humanity is, you know, in severe danger from drinking water at these levels, and we are. I think all of us are drinking water above these levels, to be honest. But what we have to hope is that when these guidelines are set, there are a lot of precautionary assumptions that are used to protect the public, so that they are really sure that if you're exposed at just a few picograms per litre, there will be no effects. They have to be really certain, so that at exposures above that, there's potential to be effects, but we just have to hope that the precautionary assumptions that are used offer us some additional protection. But it is of concern, but we can't really know whether these effects are occurring right now, because there's not been enough sort of research to do done on this, and we just basically going forward we'll just have to live with this uncertainty, whether if the effects are occurring, and it would be these, you know, because as the guidelines are set on this immunotoxicity, there would be the effects that we might expect, but you know, but it can be quite hard to even show that these effects were occurring because there's no real control population where people are not exposed to PFAS. Everyone's going to have this low-level exposure to PFAS. One thing that might console us a little bit is that we have been exposed to higher levels of these 4 PFAS in the past, and the levels in human blood have actually dropped. So in the actual levels in human blood peaked about 20 years ago. So the levels now have dropped a few times since then. So that might console us a bit that the levels, you know, in blood have gone in the right direction. I don't think this drop will continue forever, because I think what happened was that we removed some important exposure sources around the turn of the century, which caused this huge drop in exposure, but eventually the background environmental exposure is going to take over, and then I'd expect that human blood levels will not drop anymore. They'll start to level off in the same way that the environmental levels have leveled off. But we haven't really seen that yet in the data, but that's what I would expect.
Mm-hmm. Yes, absolutely, and you are one of your many research focuses with PFAS is its atmospheric fate and its fate in the atmosphere, which is quite unusual and part of the reason for these stable rain concentrations. So could you explain a little bit about how PFAS acts in the atmosphere and interacts with rain?
Yeah, this is quite complicated. So there are basically three major sources of these four PFAS that we mentioned in our paper. So I mentioned earlier all these so-called volatile PFAS. These were used in a lot of consumer products. So these include things like fluorotanimate alcohols. These are very volatile. They were used in, say, rain jackets and carpets for these fluorotanimate-based products, at least, were used in these kind of consumer products, and so impurities have leaked out of these products, and some of these impurities are these very volatile substances. So these are everywhere in the atmosphere, these volatile PFAS, and they're also continuously being emitted to the atmosphere still from waste sites, for example, landfills, and maybe also just passively diffusing out of environmental media like soils and so on. And then in the atmosphere, these volatile PFAS, they degrade by a very complex oxidation process into these four, some of in case of the fluorotanimate alcohols, they degrade into PFOA and PFNA. But then there are other precursors, legacy precursors that were made by a big company called 3M, and these volatile precursors can degrade into PFOS and this hexane sulfonate compound that's also mentioned in our paper. So this is one source of these chemicals to the atmosphere. The second source is something that we've been studying a lot, and this is the resuspension of PFAS from the ocean on what's called sea spray aerosols, sometimes called more generally as marine aerosols. So what happens is when you have waves in the ocean, this entrains air, and you get bubbles forming in the water below the waves, and so you have a whole spectrum of bubbles. And because of the surface active nature of these PFAS that we mentioned in our paper, so surface activity, they're like detergents. They have a polar head and they have a hydrophobic tail. So they have a head which loves being in the water and a tail that hates being in the water. And so what happens is that they go to the bubble interfaces, and so that the part that's likes being in the water sort of points into the water, and the part that doesn't like to be in the water goes into the airspace in the bubble. So you get an enrichment on the bubble films, and this enrichment is really strong for these super surfactants. So when the bubbles rise to the surface and then burst, they eject highly enriched droplets into the atmosphere, and these droplets are very small. They're like micrometer in diameter, and because they're very small, they can travel very long distances in the atmosphere. As I say, highly enriched with PFAS by up to 60,000 or even more times compared to the levels in the water below. So this seems to be a very important transport mechanism for these PFAS that we studied in the paper. And so it's something we're studying intensely. We think could be comparable to some of the other sources to the atmosphere, and also a very important sort of long-range transport mechanism for these chemicals. And then finally, the third source is the direct emissions of these chemicals into the atmosphere, which is still ongoing. It used to be ongoing pretty much everywhere in the globe, but now it's mostly in China, where they're still making fluoropolymers using PFOA and PFNA, and it causes very large emissions into the atmosphere. And so that's one of the reasons why the highest concentration for PFOA in rain is near a PTFE manufacturing plant in China. So you're going to get very large concentrations in the air near those fluoropolymer manufacturing plants. So those are the three main sources, and then in the atmosphere, they're going to be transported around on the PFAS that we study in the paper are not volatile, so they're going to transport some distance in the atmosphere. depending on the size of the particles they're attached on, and then they'll be washed out from the atmosphere on, for example, on rain. But there will also be there can be dry deposition of them as well. So they're quite complicated science, but it's something that we're studying in quite a lot of detail in our research group.
Mm-hmm. Well, thank you. No, and then yeah, so you mentioned, and now that with this ubiquitous presence in the atmosphere in rain, you mentioned also in your paper how this is a source of contaminating soil and therefore vegetables, and also, of course, drinking water. It can enter surface water and be one of the sources there. But maybe could you talk about these how it interacts with other sources of PFAS? I mean, is it only through the atmosphere, or in our drinking water and vegetables, do you expect also other sources of PFAS?
Yeah, I mean, for soil, for example, the sewage sludge or biosolids application is going to be an important source. So this is, in my opinion, something we shouldn't do. I mean, I don't think we should do it generally because of all of the chemicals that are in that particular matrix, but in particular, these extremely persistent chemicals are going to be problematic when you apply sewage sludge to soil. To surface waters, there's also multiple sources. You still have quite a lot of PFAS going through wastewater treatment plants because we use a lot of PFAS still in consumer products, not these old 4-PFAS, but there are lots of replacement substances which are still used in our consumer products, which we'll use in our homes, but will end up going down the drain into the wastewater treatment plants. And then there's also industrial uses of PFAS still ongoing, which also either go through some kind of industrial discharge into the surface waters, or depending on the industry, can also be connected to municipal wastewater treatment plants, and can also be emitted in our municipal wastewater. So yeah, there are multiple sources of PFAS that we have to consider. It's a complicated subject.
No, absolutely. And then maybe we'll start to I'll ask you some questions about what we can do about this global problem that has exceeded a planetary boundary. The first question is it possible to remove PFAS from water, soil, or other matrices through technical means?
Yeah, this isn't my major area of expertise, but I am aware that there are many different techniques now being developed for removing PFAS, different kinds of PFAS from both water and from soils. So the oldest technique was activated carbon, and that works pretty well for these 4 PFAS that I mentioned in my paper, but you have to, of course, regenerate the activated carbon, and you also have to think about what am I going to do with this contaminated activated carbon after I've used it. So there are problems with that, and it only really works for the longer chain perfluoroalkyl acids, like the ones in the paper. And when you have these shorter chain acids, which are the replacement substances that have replaced the old ones, these tend to just go straight through the activated carbon treatment. So then they've tried scientists working on this have tried other techniques for these shorter chain substances, such as ion exchange resins, and these work a little bit better for the shorter chain substances, but not perfectly. And then there are other techniques, like probably the best technique, as I understand, is this reverse osmosis technique that seems to work quite well for both short chain and the longer chain acids. I think the problem with all of these techniques is, that they're not traditional treatment techniques. They have to be implemented into the current wastewater treatment processes. This is going to cost money. Some of them actually have quite high additional energy costs associated with them. And it's uncertain whether you can really treat all of the PFAS with these different techniques. And then for soil, there are also various techniques being developed. For example, soil washing, where you wash the soil and then treat the washing water. But of course, you can imagine this is also extremely energy intensive. Actually wash soil and then treat the water that's created from this. So And then these contaminated sites where you have huge areas of soil and groundwater contaminated, again, you may have to excavate the soil, you might have to pump up the groundwater and treat it. And again, this is very energy intensive and going to cost a lot of money. So there's a lot of effort being put in to try and find methods which are both effective and also require less energy cost. And this is, of course, a big part of ZeroPM, which is not my particular area of expertise in ZeroPM, but this is an area which is going to be addressed by this project in a lot of detail.
Yeah, well, thanks so much for mentioning ZeroPM, and we have definitely colleagues at TWZ in Germany looking at that, and I know with the funding call that got ZeroPM, that's looking at these persistent and mobile substances, including a lot of the short chain PFAS that you said, that we know very little about and are hard to remediate. This is a major focus. So if anybody's interested in research about these short chain PFAS, definitely check out ZeroPM and the sister projects. Thanks. And what would you say should be like the major lessons learned going forward? Like what should we do about PFAS and maybe more broadly other persistent and mobile substances or persistent substances that are capable of this global exposure?
Yeah, well, I'll start by just saying that going back to the planetary boundary problem is that any chemical which is persistent and mobile has the potential to be a planetary boundary threat, because they're going to stay in the environment and become global contaminants, because they're going to spread and they're going to stay, and then they're going to be poorly reversible. So all of those chemicals have those problematic properties. Regarding PFAS, the paper focused on 4 PFAS, and we know there are many thousands. In fact, that number is growing. Seen Emma Szymanski's work, there could be potentially millions of PFAS that have been made, but there's probably only thousands that have been used in substantial quantities. But there's still thousands, and as I said, we only focused on 4, and we don't really understand all of the properties of these substances, because we only monitor a few and we only study a few. So there's definitely more surprises to be discovered regarding some of these other PFAS, and so if we just carry on using them, we're going to discover more problems. So my suggestion is that going forward, we have to be more precautionary with persistent substances as a whole, and especially persistent mobile substances. But I think persistence is a problem in itself, and all PFAS are highly persistent. So let's consider these uses going forward. And in my opinion, and in the opinion of my co-authors, we and probably a lot of the people in ZeroPM, is that we have to be precautionary going forward using these substances, and only use them where they really needed or essential. So where and the essentiality of each use needs to be assessed, and only where they're essential for health and safety, or they have some other critical function for society, should we continue to use them. And so that's going to require some thought and assessment. And then we have to, instead design safe and sustainable chemistry. I think there's a big movement here towards green chemistry, making chemicals which are designed for degradation, so that when they enter the environment, they degrade into safe end products. And there are a lot of good actors in industry, and they hold the solution. And especially in the Nordic region, I'm delighted to see that there's a lot of companies and retailers, chemical manufacturers and retailers who have signed on to the PFAS movement and are really committed to phase out PFAS from their products and from their supply chains. And that movement, we need to grow that movement, and then I think I start to feel optimistic about the future of the planet.
Well, that's great, and thanks for ending on that optimistic note, because I mean I think a lot of people could read this paper and think new it's a new doom and gloom story, but it is that, but it's also an opportunity to learn, because thankfully, we diverted maximum use of these very problematic PFAS early on, and this has helped, and we can learn from that, and we can find solutions to prevent crossing this planetary boundary with more chemicals. And I hope also, since your paper had such a broad outreach, that it might have reached new audiences so that more people can be aware of this problem with persistent substances and PFAS, and so they can think about that in their daily life in terms of, can I avoid these substances in my daily life, or can I influence local policy makers or industry to phase out these substances? Because this is part of the way that we can protect future generations from PFAS and other persistent mobile substances. Well, Ian, this has been great. Thanks so much for your time. I learned a lot about your paper, and I hope a lot of our viewers did too. And thank you so much. This is Hans-Peter Arp from ZeroPM.
Thank you.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.
Great. Yeah.
That really gives a proper overview.
Excellent.
Isn't it?
Very good.